Okay, guys, acid-base chemistry. By the way, we mentioned Breaking Bad last time, or a couple of times. You may have also heard of the series called Barking Bad. See a little fellow there. He's got his eyeglasses on. It's very important.
Is he drinking in lab?
Doing?
Is he drinking in lab?
No, that's a flask. I don't know what he's doing, but he's
He doesn't have a lab coat.
he's not drinking. If you look closely, it says Jack Daniels on that mug. Okay, the key will be posted on the third floor as you start walking down towards the labs. There's a glass case in the hall. As soon as you start walking down the hall towards the labs, that's where the key will be posted. Acid-base chemistry. Any questions about lab tomorrow? Lab reports due tomorrow and Friday. Any questions? Any questions about anything? How are we doing with the videos? I see there's not a large number of people watching videos. There's a viewer count. How many watched? 4. I'm surprised only 4 people would rewatch your lecture. But, question?
I was just going to say, can you make a majority of the test nomenclature?
There will be a nomenclature question, yes.
Dr. Stevens, can you do a complex example with the alkane nomenclature? Can you just do a complex one example, please?
Good, I'm glad you're ready to ask questions. We'll be getting to that handout after this one. Ask again, let's do it then.
Okay.
Or stop by. Anything else? Anything else? IR, how are we doing with IR? You'll be running IRs this week in lab. Instructions for running IRs are in your lab manual. You do not have to write those in your lab notebook. Take the lab manual with you to the IR room. You will be expected to run IRs on your own though. If the instructions are not clear, please ask. Acid-base mechanism. How we doing on this here? Anytime you do an acid-base, you got to identify the strongest acid and the strongest base. Right? Strongest acids, that's what we're talking about right now. How do you identify strongest acids? We left off here. This alcohol is more acidic than this one. This one has sort of like 3 lines of induction. They all kind of add up to go into this carbon, and this sort of, they all come this way towards this group. This one only has 1, so it's not as bad off. This is more acidic. Which one's more acidic here? Difference, fluorine or chlorine? How'd you do on this one? I assume everybody has made their choice here, right? Who said left? Okay, who said right? Who did not vote? Okay, more acidic? This guy here. Yeah? Why?
Wait, why would you see a larger?
Why did some of you say this one?
Larger.
Was what? What does larger have to do with this? Do what?
They're both group 17.
But isn't that just with HCl and H fluorine?
That's when the charge is on the atom. Is a negative on the atom? Is a negative on the chlorine? No. Size is only when you make the Y larger, it makes the charge more spread out. How would this being larger make this charge being more spread out? It wouldn't do that. All you have here is induction. First off, we're obviously considering the anion, right? Okay, what does F do inductively? Pull, donate, withdraw, donate? Pull. What does chlorine do? Pull. What's the difference? One pulls more than the other. Which one pulls more? Chlorine pulls more. It's more electronegative. It's pulling more of the minus away from the oxygen, getting the oxygen more towards neutral. So this original alcohol is more willing to become minus. Because it's actually not as much minus as the other one is. How about this down here? What's the difference? Minus, minus. They're both pulling. Is there any difference here? Yes. The inductive withdrawing of the group like this does sort of diminish as you get further away from the business end. So it's not exactly like tug of war. You had a rope, no matter where the end person was, it'd still affect the whole thing. But here, the fluorine is further away, it doesn't affect as much. The inductive withdrawing diminishes as you get further away. So this one's more acidic. That original alcohol is most acidic, that original alcohol is most acidic. There's some commentary on the right. Number 3, by the way, what was number 2? Organize your thoughts. If there's a 1 through 4, I would probably make sure you know what 1 through 4 is, right? That organizes your, okay, what was 2? I forgot. Induction, right? Yeah, and the examples were about induction. That's your starting point, because if you never realize you're doing induction, you're kind of missing the game. And I try to make my handouts organized, but if you don't pick up on that and take advantage of the prompts and the, all right? What's number 3?
Resonance.
Resonance effects, yes. Resonance. Look at these two OH compounds, okay? Which one's more acidic? Well, we got to consider the conjugate bases. Okay, which conjugate base is most stable? You can actually get the answer from induction. I mean, there's really nothing withdrawing here. If you want to consider one of these carbons anything, it's donating. That carbon donating. But you do have the oxygen here. And it's pulling away. And even though it's a right turn there, it's still pulling away from the oxygen. And that right there should tell you which is more stable, right? Left or right?
Right.
Correct. I mean, this is a wash. This is equal. That pulling away should make that more stable. But that's just an induction argument. Well, it's kind of not induction because it's a pi bond. Induction is single bonds, right? But that wouldn't get you the answer. But the major answer here is resonance. Now, I'm not going to just read this here to you. This is the extra free information. I'm going to tell you in a different way, like Cliff Notes, etc. Then allow you to read this, put it together. We have resonance here. And we will see resonance as we go along, here and there and everywhere. Okay, I reckon we can look at this. What's the hybridization of this oxygen and thus the lone pairs? What type of orbitals are they in? This oxygen is what? sp3. LPs in what type of orbitals? They're all in sp3 because an sp3 atom does not have any other type of orbital. Okay? What's hybridization of this oxygen? sp2, correct? sp2. And one of the lone pairs is in what type of orbital? One lone pair is in a p orbital. The original had 2 lone pairs. The Conjugate bases each have 3. So it's like the oxygen gets an extra long pair when it becomes a conjugate base, right? Here's kind of the take home. If the extra long pair, if you can give it something to do, you can stabilize it. This is essentially, the extra long pair here is the one that's in the p orbital. It really is it the extra one? I don't know. One of the 3 is in a p orbital. We can say it's the extra one. But by it being in a p orbital, it's very stabilized by conjugation. What is conjugation? That lone pair that's in the p orbital is lined up with the next door p orbital. And so we put one of the lone pairs, let's say the extra one here, but look over here, there's a p orbital there, there's a p orbital there. Now that's one electron, that's overlapping to make pi bond, which you see there. But the extra lone pair in a p orbital, we can now have 3 p orbitals lined up. And so we essentially, the extra lone pair has something to do. Lining up with the orbitals is a very stabilizing effect. The p orbitals lining up is called conjugation, or broadly, resonance. Now, is the extra lone pair here on a p orbital doing that? The answer is of course not. That atom doesn't even have a p orbital. So how could that be going on? This has the p orbital game that could be happening. Very stabilizing. That's resonance. Questions?
Okay, so on the oxygen, you said one lone pair is in the orbital, but it seems like you need 2 of them in the orbital. You see what's
No, I do one p orbital, I put one lone pair in the p orbital. There's a p orbital, that's a lone pair, one lone pair in p orbital.
where's at the bottom?
What do you mean?
So like it's 2 sets of lone pair in one p orbital? Is that what you're getting at?
You're talking about that was already drawn?
Yes.
No, I didn't redraw that. I mean, those are in hybrids. This is sp2.
Okay.
You gotta know what sp2 is. sp2 means there's 3 hybrids and there's 1 p orbital. I mean, we spent a good amount of time on that last week. sp2, right? sp2, boom, 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 p orbital. What do we see if we graph this? In this situation, I see sigma bond to carbon. Here, this is oxygen. I see 3 lone pairs. The 3 lone pairs are here. 2 of them is in a hybrid, and 1 of them is in a p orbital. I drew the p orbital and put the lone pair in it to show it interacting with the neighboring.
Yeah, no, I guess that.
Okay, then you got it. What was confusing?
No, it's okay. I'll just put the argument.
Keep asking. Other questions? The starting point is understanding sp2 and all that from last week. And if you ain't ready to go on that, then you can't understand this. But guess what? Next time we talk about this, we'll take it a step further. And if you're still figuring out hybridization, well, then you're going to get more and more behind. That's resonance. And that's why that one's more stable, and thus this one is more acidic. What functional group is that? Carboxylic acid. Yeah, it's acidic enough that it's called an acid. That's just an alcohol. pK of this is about what? About 4. This alcohol? About 16? Yeah. Like water? Good. Okay, you can draw resonance structures. That's basically what's going on. The p orbitals are interacting. But we show this by drawing different resonance structures. Resonance structures are just alternative Lewis structures, where the only thing that's been moved is pi electrons. And we use our intuition, our chemical foundation. For example, these electrons can be moved towards oxygen. Does that make sense? Does oxygen like electrons compared to carbon? Yeah, so you got polarity here. We can move the electrons towards the oxygen, pi bond, and we can get this structure. That's actually just the resonance structure. Now, on day one, we may have drawn this and said, hey, carbon doesn't have an octet. So what do we need to do here? And we move these electrons down here and make the pi bond. Well, that would have taken us back to this. That doesn't mean we can't come this way and show a different, okay? Now, this is a better structure, yes. But this is still a resonance structure. Now, but look at here. Instead of bringing these down and making pi bond there, why not take these and move them in here and make pi bond there? Why not do that? Well, the answer is all the above. This is all there. Now, what resonance is it's sort of extended delocalized bonding. You really have bonding all through here. And ultimately what you have is what we set up there. You have p orbital, p orbital, p orbital. P orbital, p orbital, p orbital. You have a lone pair. And I just drew it up there. But in organic chemistry, we tend to show these real structures called resonance structures. They're actually fake. None of them are actually a true representation of the molecule. But it's the way we showed. Now, again, a more true representation would be to show something like this with partial bonds. But this can be very cumbersome, especially for you at the beginning level. What is this? Well, it's really a bond and a half between each oxygen and carbon. You really need to read this and start reading your textbook, etc., about resonance, and addressing it systematically through your reading and understanding. This is a summary. What I started with is sort of the business or the take-home. P orbital, lone pair, interacting with neighboring p orbitals. And think about it. There's a single bond here between C and the O. If this p orbital starts interacting with this one, that's more like a second bond. It's more like double bonded now. So is it or isn't it? Is it single or double? Well, it's actually like somewhere in between single and double. If you're saying it's single, then what type of bonding do you get from this interaction? Because a single bond is there. If it's only single, then what does this add to the game? That's pi bonding there. If you're saying it's only single, then you're disregarding that's going on. Well, not really. It is going on. That's why when we draw the so-called hybrid, it's really like a bond and a half between here, because you got some of that pi bonding. Okay. Resonance is a very important or major effect. And often outweighs other effects. For example, look at these two compounds. Forget about pKa's. Which one's more acidic? Well, this is CH's and NH. This is CH and OH. Which compound is more acidic?
The first one,
Why this one?
the pKa is lower.
Based on structure.
It's got the acidic H.
So you're saying you'd rather form a minus on N than O? Which is more electronegative, N or O? So where would you rather form minus? I mean, when, in the previous page, yesterday or whenever, we preferred, yeah, O is more electronegative. You might want to say O minus. But actually, this is more acidic, because if you look at the pKa, it's actually more acidic. Why is it more acidic? Why is it more favorable to have an N minus and an O minus? Resonance. Because if you look at the conjugate bases, right? does this oxygen have any resonance? That is a lone pair in a p orbital? No, it's sp3. There is no p orbital. No resonance. No delocalization. None of that. What does this here have? Resonance. You got p orbital here. You got p orbital here. P orbital there. Well, guess what? One of these lone pairs is going to be in a p orbital. Why? So it can interact not only with one, but two. So it's like double resonance. And this p orbital interaction of the extra lone pair that the nitrogen took on is a very stabilizing effect. And it's actually trumping or outweighing the electronegativity of the oxygen. Even though it's less electronegative, it's more stable because of resonance. Yes.
Does resonance always outweigh?
So you're thinking that no, you got some apples and oranges here. You got to be careful. That's an example. Always? No, not always. Because guess what? If we go back, which is more acidic, this guy or HCl? So what's the conjugate base here? Just Cl minus? It's just Cl minus. Which is more acidic? Well, this anion has lots of resonance. There's no resonance here. Which one's more acidic? HCl. So that's a case where the resonance did not make it more acidic. That's because here the chlorine is so electronegative. It doesn't need resonance. So there's a case where resonance did not make it more acidic. Okay, number 4. Hybridization effects. Look at the acidity of these CHs. Can CHs be acidic? Sure, anything with an H can be acidic. Are CHs strong acids or even mildly strong? Or? No. They're rarely acidic. That doesn't mean they can't occasionally act as acid, and that doesn't mean we can't rank them. Acidity for CHs, and it depends on the hybridization of the carbon that the H is attached to. The SPCH is more acidic than an SP2CH, and that's more acidic than an SP3CH. For example, that H is more acidic than this H, and that H is more acidic than any of these SP3CHs. Why? Well, we really need to consider the conjugate base. What's the conjugate base of this? The anion. Again, I bet only half of you could show conjugate base. Please. When the test comes around, please make sure you can show conjugate base of any acid given. Right? Why is this conjugate base more stable than a conjugate base over here? Hybridization. What is the, we can say the hybridization of the carbon, but let's focus on the lone pair. This lone pair is in what type of orbital? SP, correct. This lone pair is in what type of orbital? SP3, correct. Okay. Which lone pair? Now, lone pair is sort of extra. It took on a lone pair. But which lone pair is more stable? One on the left. Now, maybe you just arrived at that because this is more acidic. That implies that this conjugate base should be more stable. So I don't know if that's why you said this one. But let me ask you then, but why? Why is that one more stable?
Because the
Electrons are closer to the nucleus. Now, perhaps you read that there.
There you go.
Okay? This lone pair is in an sp, which is 50% s. Okay? That's only 25% s. 50% s means the orbital, if the electron's in that orbital, is going to be able to be closer to the nucleus. And the closer the electrons are to the nucleus, the more stable they are. Because the charge is less separated. Okay? Closer to mama, more stable. Okay? Lone pair is closer to mama here. It's further away there. This is a hybridization effect. It's not a difference in electronegativity. They're both carbons. There's no resonance here. Purely a hybridization effect. Very important. That'll be applied to nitrogens a good bit. Because nitrogens we often consider as bases. Speaking of bases, let's look now at them. Now, Jen, you learned, I think, that bases accept protons. Is that right? Yeah. I recommend you forget that terminology. Bases take protons. They don't accept them. Accept them sounds like they're just staying there and it's like you threw one at it and accepted it. It's totally bad for thinking about mechanism and how the chemistry takes place. It takes them. It actively takes them. Does something. I have to do something to take it. Okay? Bases take protons, Bronsted-Lowry. Now, any acid-base reaction's got to have an acid and a base. So, I mean, here's an acid. What's going on here? If this reacts with this and get those, well, the CH3 has now taken an H there. So this takes an H from water. Now, I typically would circle the lone pair. These electrons bond to the H. These electrons move on to the oxygen. We now created this bond right there, right? When the C bonded to the H. The lone pair bonded to the H. Those two electrons used to be a lone pair. That arrow is done. What does this arrow mean? These electrons move on to oxygen as what?
Lone pair.
The third lone pair. It's now separated from the H, and you generate that. Well, what we just did, and anytime we do an acid-base reaction, we'll do the same thing, is just an example of what we showed last time, right? There's your acid-base mechanism. That mechanism applies what percent of the time when you do an acid-base? 100% of the time. Not 99, 100%. We just did that there, and that's how you're able to generate the products. So down here, what's the acid over here? One of these is an acid, one is a base. Obviously the acid is this guy, right? What's the acid? It's the thing that has the H. What do you want to call this thing? The base. It's the thing that takes the H. Okay? All right. We'll talk about pKa's. I went ahead here. Each side's got to have an acid. The acid over here is 16. Just about any acid base is really going to be in equilibrium. Now this equilibrium is so small in this direction that it's about that, like that. But it's an equilibrium. That is, this reaction can go that way. Over here, what's the acid if it's going that way? That's the acid over here. It's the thing that has the H. And that would be the base. But the reaction's not going to go that way because we know how to use pKa's to judge equilibrium. In the example above, the base was an anion. The base doesn't have to be an anion. Down here, the base is neutral, ammonia. It can react with water. Same exact mechanism, which applies 100% of the time. These electrons take the H, These electrons move on to oxygen. Okay? When that bonds to H, you now have nitrogen bonded to 4 hydrogens, and I drew that sort of condensed. It's a positive charge. Of course, in any acid-base equilibrium reaction, one species is going to be neutral, one species is going to be charged. Neutral, charged. All this is consistent, right? This is the acid on this side, that's the acid on that side. That should all be a review from all your previous acid-base work. Let's predict base strengths. Which is a stronger base, ammonia or methylamine? Which is a stronger base? Yes, methylamine, right? Why is methylamine a stronger base? Because what? Why is methylamine a stronger base?
Is it because it has donation of the carbon?
Well, it's likely due to the extra thing that's here. What's the electronic properties of this carbon?
sp3.
Hybridization is sp3, but what does it do? What's its consequences, or how does it influence?
Electron donation.
An sp3 carbon donates? Donates. What's that going to do to the electron density of the lone pair? Increases, right? And if the electron density of the lone pair is increased, is that going to make it more attracted to the partial positive H? Yes. You guys know, right? For bases, the lone pair is the business end, right? And you have electron density. And the more electron density, the stronger the base, right? You know that, right? So we're talking about electron density of the lone pair. This lone pair has more electron density because it has a methyl donating. Electron density may be like a bank account. Okay? You got 2 bank accounts here, but this guy has a rich friend donating money towards the bank account. What's that going to do to the bank account? Going to make it more robust and more money, more electron density. Number 2, which is more basic?
Right.
What's the difference here? Difference is this. This lone pair is in what type of orbital? sp3, correct. This lone pair is in what type of orbital? sp2, correct. Which one's more basic?
What?
Yes, that one, right.
It's opposite.
Why? Because it's further away from the nucleus. How's that going to make it a stronger base?
Makes it a weaker acid.
I wouldn't.
What's like the opposite?
What do you mean it's a weaker acid?
Like, you know, if it were an acid, that one is farther
Yeah,
away, so
but-
it wouldn't be the strongest acid, which means it would be the strongest
I don't quite
base.
understand why you invoke that. I mean, I think you may be referring to conjugate acids.
Is it wanting to accept more, like, take more protons?
The closer the lone pairs to the nucleus, the more stable it is. Okay. The more the lone pair is away from the nucleus, the more it's going to get out there and find an H. Okay. All right.
Wow.
If the lone pair is held tight to the nucleus, it's sort of just held there and it can't do much. Okay. Lone pair out here, electrons, charge separation. There's more charge separation, it's more minus. Oh, proton, boom. Versus, I'm happy. Okay. Hybridization. Lone pair is closer to the nucleus. It's going to be less basic. There's others here to do. Basically, you got to find an argument to support your answer. We can use the same arguments you did with the looking at acidity. Because really, when we looked at acidity, we considered the conjugate bases. And what we were really doing was looking at, okay, the more stable the conjugate base was, the less basic it's going to be. Which is a stronger base? Right or left? Which is more stable, right or left? Right, more stable. Okay? That means it's more willing to exist like this than this. This don't want to exist like this. It wants to find a proton and go back to that. It's a stronger base because it's less stable. So you're using the same arguments, you're just understanding the difference between acids and bases. Okay, we'll see you downstairs tomorrow.